So my name is Salomon Brys, and I'm going to be talking about using C and C++ and Rust and whatever you want, basically native library, and using that in a Kotlin Multiplatform project and embedding it in a library so that you can distribute it. So let me start off by saying that I lied. I said that this talk was going to be a live coding talk. There's 40 minutes, so it's not going to be a live coding talk. Basically, what I'm going to do is show you some code and hope that it works. Also, because it wouldn't be really fun otherwise, I'm going to build and launch unit tests live. So, you know, what can go wrong? And I'll be running, starting the test before explaining what it does so that I can explain while it builds. So, what are we going to build? So why would you want to embed C and C++ or Rust or whatever, or a native library into your multi-platform library? Well, there are plenty of use cases, and I took one. This one is about cryptography. So what we're going to do is provide cryptography primitives for our library for Kotlin Multiplatform. And we are going to provide 3 cryptography primitives. So SHA-256 is a simple hash function that exists both on Android and on iOS, and it's provided on iOS as both an Objective-C and a Swift library. So yeah, it's pretty easy. Then we're going to use SecP256K1, which is an elliptic curve that's used by Bitcoin and other projects, and it's provided as a C library. So we'll deep dive into how we can use this C library that is not provided by the system, and use it on Android via JNI and on iOS via C Interop. And finally, we'll provide in our library ChaCha20 Poly 1305, affectionately known as ChaCha Poly. And this library is a new cryptographic hash function. This function is a new cryptographic hash function, and it's provided by the system, great, except that it's not provided on iOS as an Objective-C API. It's provided as a Swift API, and Kotlin cannot talk to Swift. So we'll see how we can use this Swift function in a Kotlin Multiplatform project library. Okay, so stage 0, create a KMM library project. Each time you see this star, it means that I'm going to dazzle you with some code. So let's start. So first of all, it ran. It worked. We have our unit test. So what did we build? When you create a KMM, Kotlin Multiplatform Mobile, so KMM library, you have to use Gradle. And for some, it's a bad news. For some, it's just news. It's never really a good news to use Gradle, but I happen to really like Gradle. It's a very performant tool, but it's a pain to learn and a pain to debug. Yet, you have to use Gradle, and I'm not going to go into too much detail. There are talks. There was just a talk introducing Kotlin Multiplatform. So you create a Kotlin Multiplatform, and you define that you're going to build a library for Android, a library for iOS, and look at that. And I also for iOS simulator for Mac M1 Silicon, because iOS doesn't provide at the moment. When you use the iOS target, it's just for x64 and regular ARM64. You still need to configure iOS simulator ARM64, and basically that's all I'm doing except that I'm saying to Gradle, print on the standard output the result of the test. And so what I'm doing here is, in command main, I have this SHA-256 function, and it's basically Kotlin code manipulating bytes, and in command tests, I test that. Now, what's really important is to notice that when I'm running the tests, it runs on iOS and on Android, and it even runs twice on Android because it runs for release and debug, which is to my opinion, useless, but it runs on iOS and Android, and it's not because a code is common that it will perform the exact same way on Android and iOS. JetBrains told you so, they lied. What is actually happening is that they're doing their best so that it works the same on both platforms, so yet you need to test. Okay, what am I doing wrong here? I am writing my own cryptography, which is a huge security risk, so never write your own cryptography. So wouldn't it be swell if I could use the system SHA-256 library? So for that, what we're going to do is expect the platform to provide us with a SHA-256 implementation, and we'll use that implementation. So first, we define that we expect a function. Note the expect keyword. We expect the SHA-256 function to exist, and it returns a SHA-256 interface. And what we do is we implement this function in both Android and iOS as actual functions. Now, here you'll notice that I use expect function and actual function rather than expect interfaces and actual interfaces, or expect class and actual class. I would recommend staying away as much as you can from expect interfaces and expect classes unless you know perfectly well why you are using them, and stick to expect function, which are a lot easier to reason about and to use. So use expect interface and expect class only if you really need to have different interfaces and classes in your platform code. But if you can use expect function, you should stick to expect function because they are way easier. So we all know how to implement this in Android, right? Android provides this as a Java/JVM/Kotlin API, so it's really easy to abstract SHA-256 as a JVM function. iOS is something entirely different. In iOS, when you're writing Kotlin code for iOS, you are basically writing Objective-C code, but with the Kotlin syntax, which means that you are submitted to the Objective-C constraints. And that constraint is that you need to allocate and free and manage the memory. It's not JVM memory, it's platform memory. It's, we're going back to the old age of C. So Kotlin provides a way to allocate memory on the native heap, and then you can simply access the pointer of the memory you've allocated and pass that to a function. Note that this function, cc SHA-256 init, is a function that exists in Objective-C provided by iOS. And what Kotlin does is that it provides you with all platform Objective-C function and classes and allow you to use them directly in Kotlin. And we'll see that just in a bit. So what we need to do is find a way to provide, to write the data into JVM memory, because we are going to get this byte array as a JVM memory. So what we do is we pin the byte array, and then we can access its address and provide it to a SHA-256 final function. Pinning an object means that the Kotlin runtime won't move that memory around, because it's a managed runtime and it tries to optimize the memory as much as it can. So if you don't pin the object, then the object may move in memory following the whims of the Kotlin native runtime. So you cannot access its address because it may change. So you need to pin it, and then once in pin, then you have the API to access its address. And then, of course, so use pinned and use address of. And then, of course, you can you need to use update to provide the data that you want to hash. Note that this time we are not pinning input, we are using ref2, which is a smaller way to do the exact same thing, except that it will be pinned and unpinned at that when that function call is made, and so if you want to access the memory multiple times, you would use usePIND. If you don't, then you will probably use ref2. And then at the end, you need to free the memory because you're a good citizen, right? And yeah, what could go wrong? There could be an exception. So what you need to do instead of using native heap.alloc and native heap.free is use a memscope. And when you're using a memscope, then the memory that you allocate inside that memscope will be correctly freed once you leave that memscope. So let's see how it works. And I forgot to launch the check. But it's quick. Look at that. So, oh no, I didn't. Sorry. I didn't. Okay. Reset. Okay. And then let's run check. Okay. So while it checks, let me show you. What we have now here is in digest, is an expect function SHA-256 that should return a digest and an interface digest. If I'm going to Android main, then we'll see that it's implemented in the dumbest way possible because we're just creating a facade from one API to another. But if we are going to iOS main, we'll see that it is using this native heap.alloc, it is using usePIND, and it is using this function that are provided by the Kotlin compiler. Note that this function, they exist only in Kotlin native for iOS. You cannot, of course, use them on Android because they only exist for iOS. And so the test has passed just as before. And the test hasn't changed, right? The test is the same. It's a common test. We're just testing that it is compiling and that SHA-256 runs. Okay, so what is our next stage? Is to compile a library. Okay, so for Android, you need to compile the library for these 4 targets, okay, which are basically all the targets that the Android system can run on, or the mobile Android operating system can run on. For iOS, you need to target these 2, and maybe also the third one because they released a new Mac, the Mac M1, which runs on their own silicon. So compiling a C library, there are as much ways as to compile a C library as there are C libraries, right? They all compile in different way. They can use make, CMake, configure, or whatnot. So I'm not going to teach you how to compile a C library because it heavily depends on the C library. What you need to have in the end are a way to compile the libraries for all these targets. Then you can just do that, but wouldn't it be nice if you could just press run and then Gradle would compile the library for you? Okay, so I encourage you to create Gradle tasks to compile the library for you. One very easy way is to have a script, a shell script that builds the library according to the build system and the configuration that you need for the library, and then just have it as a command line in Gradle. It's pretty easy, right? Except that we can do just a bit better without having a very complicated Gradle script. We can add inputs and outputs. And as you can see here, I'm just defining inputs and outputs. So it turns out that a Gradle task can be up to date, and that Gradle can know that if a task is up to date, it doesn't need to rerun it. Okay, so how can Gradle know if your task is up to date? Simply by checking inputs and outputs. Have the inputs changed? No. Are the outputs still there? Yes. Okay, the task is up to date. I can move on. So by defining your inputs and outputs, you can tell Gradle, okay, so you're going to run this script, this shell script, it depends on all those .c and .h files, which are the C library sources, and it will output this directory. And if the inputs haven't changed and the outputs are still there, then you don't need to rerun the script, and Gradle can be efficient. So let's see how native compilation works. Here I created a... Oh, I need to update Gradle. So here I created a SecP256K1 module with a Gradle build script, and it's a bit more complicated than what I've just shown you, but basically it's the same. For each target, I create a task that executes the build iOS shell script with an environment environment variable, and then I do the same for Android. So, and the most important thing is that I declare inputs and outputs. And the goal here, in the end, you should have these outputs. You should have a static library, meaning on iOS or on macOS or Linux.a. You should have a static library that exists for each of your targets. Somehow, you need to output that. Okay? And as you can see, if I rebuild, then Gradle is not telling me, oh, because it's using configure and configure created. Yeah, so what I just told you just doesn't work. Great. Let's move. Why is it recompiling? Even configure doesn't know that. Oh, it's just recompiling one target, and now, what do you know? The third time's the charm. All compilation are up to date. Okay, so what we're going to be talking about now is how to have a lot of moving parts working together a nice way. So it is complicated, but bear with me. In the end, if it works, you'll feel like those two chaps just working at a beautiful build system and architecture. So when you are accessing native libraries for Android, you need to use JNI. And when you use JNI, it means that you first need to write a Kotlin facade. Then you need to generate headers for that facade. Then you need to write a C++ implementation of that facade for JNI, C or C++, and then you write a CMake file to compile all that, and then you need to configure Gradle to do all that. There's no better way at the moment, and there's no better way in the near future. So yeah, this is what you have to do. So let's see how it works. Let me get stage 2.1, and let me immediately run stage 2.1. Okay, so what do we have here? We now have in our build Gradle.kts file, in Android, in the Android configuration, we are declaring an external native build. And this external native build lives in Android main cpp cmakelist.txt. And here you configure that you are going to use the headers and the library that you just built. Okay? And then, where is it? You can run the tests, and you can see that it works. So, one very important thing to understand is that I didn't run the tests, I didn't run Android unit tests. And if I run Android unit test without this weird bit of code, let me see if I can do that. Verification, test, debug unit test. We should have a failure, yeah. It fails because it says that there's no SecP256K1 JNI. Basically, we built our library for Android, and we didn't build it for macOS. So you cannot run the test on the JVM. You need to run the test on an Android phone. Yet, if you run the check Gradle command line, which you should, for example, if you're using Travis or GitHub Actions as a continuous integration system, of course, every time you commit, you check the test, and it will fail. Because unit tests will fail, because unit tests are using the native library, which you did not compile for macOS, you compiled it for Android. So what you need to do is disable the Android unit test, and from now on, you won't be running the unit tests on your machine. You will be running them either on an emulator or on a physical device. And yes, I had to painfully write a C++ facade that was generated after a .h file that should live somewhere here, that is generated for me by JavaH. Now, there's another problem. JavaH doesn't exist anymore. JavaH is the utility that takes a class file and that generates C++ headers so that you can implement that header in C++. And this utility tool doesn't exist anymore. It was deprecated after Java 8. And Oracle provided a way to do the same thing with Java sources, so it doesn't work with Kotlin. And JetBrains has yet to provide anything. So what do? Well, I download a JDK 8 build, and then I run JavaH from that. If we look at local.properties, I added the path to my JavaH binary, and then in my build Gradle file, I created a task called generate JNI header that reads that local properties file and that calls to JavaH. If you find a better way to do that, please tell me. I'm deeply interested. Okay, so how does it work with Objective-C and iOS? Well, you have to write a C interrupt definition file. It's not very straightforward, but it's way easier than whatever JNI asks you to do. And then you have to configure Gradle so that it knows that the C interrupt exists and that it will build the C interrupt facade for you. And then you write a Kotlin facade. And that's the beauty of Objective-C interrupt in Kotlin native. It's that you write Kotlin. In JNI, you have to write C++. So in JNI, you write the Kotlin by hand. It generates C++ headers, and then you implement the C++ native code by yourself. In Kotlin, it works the other way around. It reads the C header file, not C++, the C header file, and then from that header file, it generates a facade automatically for you, and then you write the Kotlin facade. So you stay in Kotlin. So it's way better way to do Kotlin interrupt. And my understanding is that there once was a project in JetBrains to port this system to JNI so that it would work and it would generate the JNI facade, and that this project wasn't moved to a publishable release. So please release it. Even in a horrible state, the community will take care of it because there's a dire need for a better way than JNI. And this is a very good experience. So if we could have that for Android, it would solve a lot of headaches. Unless, of course, JetBrains is working with the pharmaceutical industries. So let's see how it works with C interrupt. In build Gradle file, now I have in my iOS definition somewhere here a SecP256 K1C interop file. And so here I'm basically saying, okay, here are the header path, and here is, and there's a C interop definition file somewhere. And what I'm saying here is that, okay, before you run the C interop process, then you should build the library. Remember, I created a build task on Gradle. So what I'm saying here is that, okay, before you run C interop, build the SecP256K1 library for iOS. Then in native Interop, I created this header file, and no, it's not an error, it's just tooling that hasn't been updated, wink, wink. And as you can see, the def file is quite straightforward. Okay, we're going to be reading these header files. Please, if these header files include other header files, ignore them if they are not in this folder, because you don't need to generate the Kotlin facade for STDC, STDIO, for example. You're going to be linking against this static library, and for ARM64 it's there, for the simulator ARM64 it's there, for iOS x64 the simulator is there, and by the way, you also need to link with this framework. So it's pretty straightforward. And then in iOS main, we can see the implementation. And as you can see here, I am working with these functions, SecP256K1 context create, for example. And that's the magic. The magic of CInterop is that this is a C function. And this C function has been transformed into Kotlin through a magical facade for you. Maybe I didn't run. Yeah, so, or maybe I think I need to update Gradle. Okay, isn't it amazing when it builds and IntelliJ tells you, no, it doesn't work. And then you start a Gradle build test, and then everything works. So, yeah, in the end, it should show me the function, let's say, indexing, process. Yay! Okay, so this function, I can come and click on them, and I can see that they were generated for me by the Kotlin facade. I even defined the package in which those functions are to be created. So I can use directly the C function in my SecP256 code. And note that I'm using the same API that I've described earlier to access memory, a native memory, and access pointer, and all that. It's the same API. Basically, the Objective-C APIs are generated for Kotlin through this tool. When JetBrains are compiling the Kotlin compiler, they are using this tool to generate the Kotlin facade for the platform API. And if we want to add a library, well, we can pretty easily, and as you can see, the tests on iOS are indeed passing. So these functions are running. Okay, so now I'm going to be talking about the last stage of our cryptography library, is to access a Swift API in your Kotlin Multiplatform library. And basically what we are doing is trying to have Android on the right and iOS on the left be cooperative, right? It's like we're in a meeting. However, what I'm going to be showing you today is also a nice way to bring Swift developer into Kotlin Multiplatform, right? Because at the moment, you cannot provide a library for Kotlin Multiplatform if it's not in Objective-C. And there's a way to provide that with Swift, and I'm just going to show it to you. So maybe it's a nice first step for iOS developers, Swift developers, to, dip their toe into the dark Kotlin multiplatform waters. Cha-Cha Poly is provided by Android, right? So what you need to do, of course, is to create an expect function, create an actual implementation of that function in Android, and then use in this actual function implementation, use the Android API, right? So let's see how that works. Except, let's not, because I've already shown you, and I'm not going to show you anything that you already know. It's an expect function with an actual function that uses JVM API to access this API, so nothing new under the sun. Let's talk about something interesting. So we all know that Kotlin can interrupt with Objective-C, and I've shown you, and it interrupts with Objective-C, and it also interrupts with C. So that's great. And of course, when Apple released Swift, it made sure that it would interrupt with Objective-C. So we have our mediator. It's Objective-C. If we can have Swift generate something that can talk to Objective-C, because we can talk to Objective-C, then we can have a translator, a common translator. I'm sure nuances will be lost on the way, but yet Kotlin and Swift can interact together. So what we need to do is write our Swift library that uses Swift Cha-Cha Poly, for example, Cha-Cha Poly, and then have Swift export this in a way that Objective-C can understand. So how does it work? This is Swift. You need to create a Swift class, and it needs to have several constraints. It needs to be annotated with Objective-C. Everything that will be exported to Objective-C needs to follow those constraints. It needs to be annotated with @Objective-C, and I'm sorry to Swift developers because it's not an annotation. Can someone remember the name? Okay, I call that an annotation, but I know it's not technically an annotation. It needs to be public. It needs to implement NS objects, and all the exported function of that class needs to be annotated with Objective-C and public. So these are the constraints. And it needs to, every function, of course, needs to return a data type, a class that is also exported to Objective-C, which is not the case of regular Swift, the regular Swift Cha-Cha Poly API. The Cha-Cha Poly API returns data structures that are not exported to Objective-C. So, of course, we need to wrap and abstract the function themselves, but also their return type. And then we need to use Xcode or AppCode. But, have you ever tried to convince an iOS developer to use AppCode? I have. Didn't go well. So you need to configure Xcode to create a Swift static library. And you need to convince it to write an Objective-C facade. So it's a configuration option. I'll show you. Oh, sorry. And then you need to configure a bridging header. And that bridging header will be an Objective-C header describing your Swift API. API that is public annotated with Objective-C and whatnot. And then you need to export the header, because what do you know? Xcode agrees to generate the header, but it doesn't want to export it. It's a bug. It's documented. Apple isn't working on that, so we need to do it by hand. And once you've done that, you need to embed the library that you just created, the static library that you just created, into your Kotlin Multiplatform library. So you need to write a C-interrupt definition file, add the Gradle compilation task, configure Gradle KMP C-interrupt, and write a Kotlin facade. Does that ring a bell? It should, because that's what we just did for our native library, SecP256K1. So basically, once you created an Objective-C library out of your Swift code, then the process of embedding it inside your Kotlin Multiplatform library is the exact same. It will read the bridging header file, it will generate the Kotlin facade, and then you just have to fill it up and use it. So let's see how it works. I'm going to start Xcode. Okay. Oh, sorry. Here it is. Okay, so here in my... Oh, it's not that project. Sorry. Let's find it here. Where is it? Playground demo crypto. Oh, I didn't. Oh. Sorry about that. I keep forgetting. So as I said, I'm not going to show you how it's done in Android because, you know, precisely because, you know. So here I have my, here I have my library. It's annotated with Objective-C. I have my data result class, which is also Objective-C public NS object. All constraints are done. And there's also a file here called Swift-Chapoly-bridging header. And this file is empty, but it needs to be here to tell Xcode to fill it. So it needs to exist, and it needs to be empty. And then once you've done that, there are a couple of configuration in Xcode that you need to follow. And the most important thing here in build phases, you need to add a run script that says, okay, you should also export in the include directory in the header file. You should also export this bridging header, which is -swift. So it's a -swift.h file, but it's an Objective-C file because there's no .h file in Swift, and you need to export that as well. And once you've exported that, you can build it, and you can build it from command line. And if you can build it from command line, you can create a Gradle task that does it for you. That runs Xcode build, and so you don't even have to build the library by hand. You can do it yourself. You can do it via Gradle. And then all you need to do is access the API the same way that we did before. And I don't think I have a lot of time to show you that it works, so let's move on. Ooh. But basically, the code is here in iOS main. Here, I use this library that I created in Swift, exported to Objective-C, used in Kotlin. Okay, so the next stage is to publish your library. Because you created your library, you need to publish it to a Maven repository, and it's that simple. You just have to... Oh. You just have to add the Maven publish Gradle plugin and then configure that you will publish all library variants on Android. And then the rest is taken care of for you. So it's that simple to publish your library once you've done it. And that's it for me. I just want to tell you that in order to further the knowledge of Kotlin Multiplatform, I created Coding Coders, which was the first company in Europe to be certified for its Kotlin training. So please be sure to check out Coding, our Coding open source libraries, which everything that I've told you here I've learned for the Kotlin open source library. And yeah, make sure to reach out, and we'll have a talk about Kotlin Multiplatform and its many, many use cases. That's it for me. Thank you very much.